Okay, well, let's get started. Today we have Kin-Fai Mok from Penn State University visiting us. He got his PhD at Columbia with Tony Hines, and then worked with Paul McEwen as postdoc in Cornell. He's talking about an interesting issue. It turns out I'm an old timer, and back in about 1980 or so, there were theories that two-dimensional superconductors didn't exist because they were on this renormalization group of some sort. They were critical state and all of this. So I was working with Mike Tinkham, who's one of the old great superconducting guys, and he said the only problem with the theory is that two-dimensional superconductors superconduct. They have zero resistance. The field has moved a long way since then. Now you can actually look at new classes of quantum materials that are ultra-thin, just in atom thin in some cases, and it really takes us into a new regime. Next week, we're Vidya Mahadevan, will be giving the talk here, and that should be very interesting too. And we also this week have the ES 295, 94. I've had a bad day here. 294 sign-in sheet for the students. Thanks.
Thank you very much for the introduction and for the invitation. It's a pleasure to be here. This is my first time in Harvard. I enjoyed the visit very much so far. And today I'm going to tell you about our recent results on probing the superconductivity in single layer of van der Waals metals. So in these materials, it's a layered metal, and the interlayer interaction is actually relatively weak, so that you can actually peel down the material down to a single layer limit, and we can study the superconductivity in this kind of material. And it turns out that there are some interesting consequences which so far has been ignored in this kind of material, which is the spin-orbit interaction, which makes it makes the Cooper pairs somewhat interesting in this case. So before I start, I would like to acknowledge the people playing major roles in this work. I'm going to present Xiaoxiang Xi, our former postdoc who did most of the work I'm going to talk about, and also two other students, Zhefang Wang and Yigang Song, as well as a senior PI, Ji Shan. I basically collaborate with her on anything. As well, also we got nice samples from bulk crystals from EPFL, Laszlo Foro and Helmut Berger, who gave us a bunch of different metallic TMDs to transition metal dichalcogenides to play with, as well as the funding agencies. Okay. So the physics in metals actually has attracted the interest of physicists since the early days of solid-state theory. I would summarize the major reason why this is the case, because here I show a block band in the first Brillouin zone of a typical metal. The Fermi energy is lying near the middle of the block band, and because of this configuration here, it gives rise to a very high density of states. And the high density of states actually favors instabilities of the Fermi surface when you have electron-electron interactions or electron-phonon interactions. So it gives rise to all sorts of interesting instabilities, such as superconductivity, magnetism, charge density waves, etc. Since the 1970s, early 1970s, actually, experimental physicists start to become very interested in making perfectly two-dimensional metals. At that time, basically, people would just try to evaporate or evaporate very thin films of metals and try to see what would happen in those days. And the major driving force for why this is interesting is because of the enhanced thermal fluctuation effects in two-dimensional electronic transitions. And the famous example is actually particularly famous this year is the Brzezinski-Kosterlitz-Dawlers transition. This is Kosterlitz-Dawlers, and who received the Nobel Prize this year. Brzezinski, actually, who died some 30 years ago, missed the prize, unfortunately. And another example, which actually for the purpose of my talk I would like to give, is the superconductor insulator transition. I took this beautiful data from Alan Goldman's group. Actually, I think it's published in the late 1980s. By evaporating bismuth films of different thickness from 4 angstrom or so up to 7.5 nanometer or so, you can see actually over a very narrow window, very narrow range of the thickness of this film, the material turns from a superconductor with 0 resistance to an insulator with infinite resistance. And this is actually a very interesting experiment, and lots of the work have been actually studied what's happening near this transition point here, the 0 temperature transition. But for me, actually, this data also somewhat bugged me a little bit, because when you go to very thin materials, in this case using this method, the material becomes so disordered that it turns into an insulator. It no longer conducts electricity well. So the question I have is that, so the major problem for this kind of materials is amorphous thin film, and it has lots of dangling bonds, so it's not chemically stable. So do we actually have crystalline two-dimensional metals and chemically more stable? And the answer is actually is yes, provided with by these 3 gentlemen with the discovery of graphene. I don't need to talk too much about graphene, with lots of interesting electronic properties, optical properties, and mechanical properties. One of the interesting area that actually graphene triggered in the research is actually to look into other two-dimensional materials. And I provide here with a sort of one famous example is a monolayer of molysulfide. This material has very similar structure compared to graphene, which is also layer structure. And it turns out that when you thin down the material to the monolayer case, there's quite a dramatic change in the electronic structure. The material turns from an indirect gap semiconductor into a direct gap semiconductor, which is best illustrated in this picture here. This is the optical image of a field layer MOS2 versus a monolayer MOS2. Here is a photoluminescence image showing that only the monolayer becomes bright in photoluminescence, illustrating the dramatic transition of the band structure. Ever since then, MOS2 is only one example. There's actually an explosion of research into all other two-dimensional crystal, all share with similar structure as graphene, like boron nitride, which is a large band gap insulator, which is very good for tunnel junctions as well as gate dielectric. Phosphorine, transition metal dichalcogenides, TMDs, which is a big family with both metallic compounds and semiconducting compounds, as well as recently people are also getting interested in the magnetic semiconductors, which is the transition metal trichalcogenides, and not much work actually, not much experimental work has been pursued along this direction. But for today, actually, I'm just going to focus on a very tiny corner in this TMD compound here, which is focused on this family of metals, TMD metals. The family of TMD metals actually has very similar structure compared to the semiconductor TMDs. It's a layer structure, which within each layer, there are 3 layers of atoms, with the middle layer of transition metal atoms sandwiched between 2 layers of chalcogen atoms. And the chalcogen comes from this group, the sulfur, selenium, or tellurium. And for the TMD metals, in this case, the transition metal come from the group 5. Transition metals in the periodic table is mostly niobium or tantalum in this case. So if we can actually exfoliate a single layer of this material, we can sort of think of it as a single layer of, for example, a single layer of niobium atoms, metallic niobium atoms, embedded in a calculation matrix, so with saturated bonds. So it looks like more chemically stable compared to evaporated fumes. Okay. A famous example in this class of metals is actually niobium diselenide. Here I illustrate its three-dimensional Fermi surface. If you look from the top down here, it looks something like this, with a Fermi surface centered at the gamma point, and also two other sheets at the K and the K prime point of the Brillouin zone. And it's quasi-two-dimensional with very weak interlayer interaction, so that it gives rise to this cylinder-like Fermi surface in the 3D structure. And the material is somewhat interesting with two instabilities in the Fermi surface. The first one is when you cool down the material below 33 Kelvin, it turns into a charge density wave, meaning that there's an extra periodic modulation of the charge carrier density below this temperature. And this is the STM image from the Hoffman group. And when you further cool down the sample below 7 Kelvin, it turns into a superconductor with zero resistance. And so far, we believe that it's the superconductivity is driven by electron-photon coupling. It's an S-wave, an isotropic S-wave superconductor. Okay. And so if we get a single layer of this material, what's it good for? Why is it interesting? From an application point of view, if you get a single layer of metals, it's very transparent optically. It's very flexible as well, so you can put on a flexible substrate like this. It may be good for applications in transparent electrodes, for example. And the second reason, which is more related to the physics I will talk about, is when you turn the material in the single layer, this is actually the structure of the material. And if you look from top down, it's actually a honeycomb lattice structure, just like graphene, except that the two sublattice sides are now occupied by one transition metal atom and two chalcogen atoms. So you break the immersion symmetry of the material. You no longer have an immersion center at the center of the crystal of this honeycomb structure. And plus that, the tantalum, or the niobium atoms, one is 4D, one is 5D. It has very strong spin-orbit interaction. So for a material which is non-centrosymmetric with strong spin-orbit interaction, we would expect a very strong spin-Hall effect in the material. And this is actually an interesting direction because it may give rise to a large spin-orbit Torque effect in spintronics devices. Most relevant to my talk is the property of superconductors. And in this material with non-centrosymmetry, as well as strong spin-orbit coupling, actually the Cooper pair wave function now can no longer be distinguished by the parity operator, meaning that the parity eigenstate is no longer the energy eigenstate of the system, so that the Cooper pair wave function, instead of a pure singlet state, it's actually turned into a mixture of spin singlet with a spatial even wave function and a spin triplet component, which is a spatial odd function here. I denote as dz here. Okay, so if we actually can, combine material with, say, magnetic substrates or external magnetic field that break the time reversal symmetry, so we have all three components needed for topological superconductivity in a single material, which is superconductivity, spin-orbit interaction, and time reversal symmetry breaking. So is it actually an interesting platform to explore topological superconductivity in this kind of material? I will briefly mention that this possibility at the end of the talk. Okay, this is the outline of my talk. First of all, I'm going to tell you our method of isolating a single layer of this material, and then present some results related to the quality of the material we are getting. And then I'm going to talk about some special feature related to the Cooper pairs in these materials. Essentially, because of the spin-orbit interaction, it gives rise to effective Ising spins in the material. So the Cooper pairs actually are paired up with electrons with Ising spins, so that it gives rise to some unusual magnetic properties, which I will talk about. So a little bit of history of how people actually attempted to get to a single layer of niobium selenide. It begins with this paper in 1972. Flint, a Canadian physicist from Simon Fraser University, British Columbia. What he did at that time is that he just used the tape, exfoliate very thin layers of niobium selenide just on the tape and directly just measure the conductivity of this material. And as you can imagine, the material is highly inhomogeneous. on this surface with all sorts of different thickness. And he saw he saw the superconducting transitions down to very thin films. So he concluded in his paper that the material, even down to the monolayer limit, is very stable in British Columbia air. Okay. But some 30 years later, Navazlov actually reported in his famous paper in PNAS at 2005. At this time, they actually tried to do a better job, but got worse result. They exfoliate a monolayer or bilayer, an albium selenide on top of silicon, and then try to put down the electrodes with lithography techniques. And what they got is actually that this films has a resistance of about a mega ohm. So basically, it's like an insulator. So what we know nowadays is that the material is not so stable. You cannot really expose in oxygen for that long, in ambient for that long time. You certainly cannot really try to do lithography on it. So it's bad for the material. So what we come up with is actually with the following procedure, to a sort of simple technique to make the material or make devices. We basically first pre-pattern our electrodes into different shapes on the silicon substrate, and then exfoliate this material on flexible membranes of PDMS, flexible substrates of PDMS, and then just align the two and stamp on it, and transfer a piece of materials like this. And then to protect it from oxidation contact with oxygen, we just cover the material by a layer of boron nitride, directly do another transfer and put on top of it. And to just, so this is actually a sort of lithography-free process, so we don't really do much harm to the material. To further reduce the harm of the material, we actually just put the whole thing inside a $72 glove bag, actually, filled with nitrogen, so that it's sort of nice, and then we can actually make reasonable material. If you work in Philip Kim's lab, they have nice glove box system, and they get very nice materials and devices as well, reported in this study in Nature Physics. Okay. So this is one example device we make. This is actually a bilayer, an albium diselenide with a source drain and then the voltage probes. And this is an image of the device. Actually, we can do Raman spectroscopy on the material to really make sure that it's a monolayer of materials. And you can actually see that as we change from the bulk material down to the monolayer limit, this Raman mode, which is corresponding to the interlayer shearing vibration between the two layers, disappear in the monolayer, showing that because there's nothing to vibrate with, so this mode disappears in the monolayer limit. So we can actually get a pretty good technique to characterize the Lie number very accurately. And a glimpse into the quality of the sample we make is when we cool down the material and then look at the Raman modes. And it turns out that actually the material is quite clean. We can still see the CDW order, or the charge density wave order, in this material. Actually, this shows the Raman spectrum corresponding to this CDW lattice vibrations. And you can see this mode here. And somewhat surprising is actually that when you go to the monolayer limit, you can see that this mode actually gets blue shift, meaning that actually the CDW lattice is stiffer. So it's actually representing a stronger CDW order. This is a somewhat counterintuitive result, which I will not discuss the mechanism too much. Besides optical spectroscopy, now we have the electrodes contacting the material, so we can actually measure the resistance. This shows the resistance as a function of temperature normalized to the resistance at 300 Kelvin for better comparison between the bulk material with the monolayer material as a function of temperature. And you can see that resistance just decreases linearly, almost linearly with temperature, indicating just metallic behavior is still maintained in the monolayer material. Some characteristic about the device, it's about the square resistance per layer, it's about 100 ohm, corresponding to some mean-free path about 20 to 30 nanometer in this case. And the coherence length of the superconductor is about 10 nanometer, so we are sort of in the clean limit in this case, even down to the atomically thin limit. If we zoom in this region here, you can see superconductivity basically remains from the bulk material down to the monolayer material. the TC is somewhat reduced from 7 Kelvin in the bulk down to about 3 Kelvin. And the transition is also somewhat broadened. We think it's probably related to the BKT transition, but we cannot completely exclude the effect of disorder on this material or inhomogeneous broadening of the transition. But for the decreased TC, we can actually understand the origin of the decreased TC quite well using this simple model. In a layered superconductor, there are two channels that the Cooper pairs can pair, the electrons can pair up. The first is the intralayer channel, represented by this lambda 0 here, intralayer pairing channel, and the other is the interlayer pairing channel, lambda 1 here. So when you reduce the thickness of the material, say in the monolayer limit, the lambda 1 is gone, so you basically decrease the effective coupling to form the Cooper pairs. And actually, this model, you can put down this model in some mathematical formula, and it turns out that this model, which is represented by this dashed line here, fits the data quite well. This is TC, this is layer number. It basically represents a quite good description to the experimental data. Another way to see that this is actually a pretty good model to describe the decrease in TC is to plot the TC in this strange way, log of something, and then 1 over the cosine of pi over n plus 1, n is the layer number. It follows a pretty good straight line for the data. So it provides a pretty good support for the interpretation using this model. Okay, so now we have a one layer thick, 2 layer thick superconductor, and what's so special about it? And I want to mention 2 things. First thing is actually now you can use electrical method, just pretty much like the Fourier effect transistor in your computer. Use a voltage to control the superconductivity in this material. And this is completely impossible in a bulk metal because once you try to put some electron on the surface of the metal, it's basically screened out within the depth of the Thomas Fermi screening length, which is on the order of few angstrom to 1 nanometer. But if you actually make the material thinner, even thinner than the Thomas Fermi screening length, now so it gives rise to a sheet carrier density of 10 to the 15 per centimeter square using an ionic liquid gate, which is pretty much like a battery in your cell phone, right? Except that it does not explode in our device. Then we can actually tune the TC by 30–40%, quite significant tuning using a few volts of gate voltage. And this is actually the phase diagram we got, this kind of device. Okay. This is actually a bilayer. Yeah, it's pretty hard to to do it in a monolayer. Yeah.
How do you know that it's electrolyte gating versus intercalation, or even worse, the electrochemical reactions?
It's completely reversible. So we just apply 3 volts and we go back, and it goes back to the. It's okay, not completely, but it's pretty well. It recovers the original behavior very well.
So iron liquid or the lithium?
No, it's a complicated. It's a really long name. I forgot that. Yeah.
Like some sort of iron liquid.
Yeah, it's not the lithium perchlorate. Yeah. And the other observation, which is somewhat surprising, which I'm going to spend the rest of the talk on explaining, is the measurement of the upper critical field in this material. The upper critical field is essentially the highest magnetic field at 0 temperature that quenches superconductivity. And this, I present a measurement of the bulk material, 3-layer material, and monolayer material under perpendicular magnetic field, perpendicular to the plane of the material. And you can see that superconductivity gets quenched by about a few Tesla of the magnetic field. The B field required to quench superconductivity in monolayer is somewhat lower because of the lower TC in the material. On the other hand, if we put the material under a parallel magnetic field, so that actually the material turns to be more resistant to the application of an external magnetic field. What I mean is that under 9 Tesla field, for the bulk material, the TC dropped by about 40%. And for 3-layer material, the TC only dropped by about less than 10% under 9 Tesla. And in fact, it drops to about 50% of the original value under 31 Tesla. So it's very resistive to the external magnetic field. And for the monolayer case, at 9 Tesla magnetic field, it just changes by about 5% or so, barely changes. And it survives up to 20 Tesla very well in the monolayer superconductor. Even the TC is actually very low, only 3 Kelvin. So this magnetic field that the superconductivity still survives is much higher than it should be. And I will explain what I mean by it should be. And so I'm going to spend the rest of the talk talking about this observation here. And I will explain in terms of the spin-orbit interaction in the material, the Cooper pairs with this kind of effective Ising spins. And I will also talk about some signatures of the spin-triplet component of the Cooper pair wave function in our most recent measurements. Okay, so to understand the superconductivity in this material, let's just first turn into the normal state of the material. In the bulk niobium selenide, it's immersion symmetric with the immersion center between the layers. Okay, like this, you flip the material down to this side, it goes back to itself. So that if we perform an immersion symmetry operation, flipping k to negative k without changing the spin, the energy of this block state should be the same. If we perform a time reversal symmetry operation, for flipping the k to negative k and the spin up to spin down, in this case, the energy still has to be the same because the material obeys time reversal symmetry. So with these two conditions come in, that means the Fermi surface is fully spin degenerate. At every point in the momentum space is spin degenerate. However, down to the monolayer case, the immersion symmetry is broken, so the first condition here is violated. And so here I plot the Fermi surface, the spin-resolved Fermi surface of a monolayer niobium diselenide. The different color here represents spin up and spin down. And you can see that at each point of the momentum, any finite momentum, the Fermi surface is spin split by the spin-orbit interaction here. You mean this case? You mean the bulk? Oh, the 2D case. So there's a mirror plane in the outer plane direction, but just the in-plane immersion is actually, so basically flipping from this side to this side, is not here. And actually, yeah, there is a mirror plane along this line here, so that, yeah, the material flip from here to here is the same. So that's why the spin-orbit interaction vanished at this point along the gamma m direction, which actually I'll talk a little bit more about that. Yeah.
That's theory, right?
This is theory. This is theory calculation. Yeah, it's not. Yeah. Okay, and furthermore, we can actually figure out where the spin is pointing to by looking at the crystal structure. The material has outer plane mirror symmetry, so that the spin-orbit field can be written as the momentum of the carrier cross the crystal electric field. The crystal electric field has to be in plane because of the outer plane mirror symmetry. The momentum has to be in plane as well, so that means the spin-orbit field is only outer plane, only pointing up or pointing down. So that the spins in this material are actually locked to the outer plane direction, either pointing up or pointing down, cannot point in any other directions. So it gives rise to effective Ising spins in this material. So it's somewhat special. So now we can go to the superconducting state, try to understand the superconducting properties. So what limits the upper critical field of a type 2 superconductor? There are two mechanisms. One is called the orbital limit. What it means is that if you apply external magnetic field to a bulk superconductor, vortices are formed. So inside the core of each vortex, this is the red cylinder here, which is the core. It's normal, the material, surrounded by some circulating supercurrent. And when the magnetic field just keep increasing, this normal cores start touching each other, then it turns into a normal metal. And this is corresponding to the case of a perpendicular magnetic field applied to a single layer of niobium selenide. And actually, what's special about this single layer material is that when you turn into an in-plane magnetic field, the orbital effect is completely quenched because there's no more supercurrent circulation because you only have one atom of materials left. So the orbital limiting effect is completely quenched in the monolayer case for a parallel magnetic field. What's come after that is actually the spin paramagnetic limit. So it works in the following way. Cooper pairs are formed by electrons with opposite spins, spin up, spin down. So what it means is that in the singular state, what it means is that if you apply a magnetic field, the Cooper pairs they are just indifferent to the external magnetic field until the field becomes so big that the pairs are flipped by the field. And this is the pair breaking field. And then superconductor is quenched in this limit. Okay. So if the material are actually like Heisenberg spins, like in a normal BCS superconductor, under external magnetic field, the electrons actually develop a Zeeman energy, which is a mu b, the Bohr magneton times the applied magnetic field. And when this Zeeman energy becomes comparable to the superconducting gap or the other parameter of the system, then superconductivity is destroyed. This is actually the spin paramagnetic limit I've talked about. So you can do a little bit of math here. It turns out that this gives rise to the famous Pauli paramagnetic limit, which is written at this simple form. And when you can actually write it down, this constants here is 1.84 times Tc in Kelvin. That gives you the HP, the Pauli limit in Tesla. So for a 3 Kelvin superconductor in the monolayer case, the Pauli limit is about 5.5 Tesla. Okay, but you sort of remember that I told you even up to 20 Tesla superconductivity is still survives in the material. Then actually, in the case of Ising spins in this kind of material, the spins are locked by this huge spin-orbit field to the outer plane direction. So if you apply an in-plane field, so 30, 40 Tesla is still very small compared to 1,000 Tesla spin-orbit field. So in the 0th order limit is that the spins, they just don't respond to the applied magnetic field. So the magnetic moment is 0. But then if you go 1 order higher, the magnetic field, the applied magnetic field actually competes with the spin-orbit field. That gives rise to something called a Van Vleck paramagnetism, which is the magnetic moment induced by the external magnetic field. So that the magnetic moment can be written down in this form, H over HSO times the Pauli times the Bohr magneton, mu b. So that now the Zeeman energy gets modified to this form. Instead of proportional to H, it's actually proportional to H squared because the magnetic moment is induced by magnetic field. When this energy becomes comparable to the superconducting gap, superconductivity is destroyed. You can work out the math a little bit, and it turns out that now it gives rise to a modified HC2, the upper critical field, which is a geometric mean of the spin-orbit field and HP. So it's significantly bigger than HP if we put HSO of about 1,000 Tesla. That gives rise to 50 Tesla of the upper critical field. This is not the full picture, which I'm going to tell you. This is somewhat naive estimate. So with this picture in mind, it basically explains the observation of the parallel magnetic field data in this case. And for the 3-layer, for the monolayer, I also write down their HP value, which is 10.8 Tesla and 5.5 Tesla in this case. So you can see that basically because of these Ising spins in the material, the upper critical field gets way beyond the HP value of each of the material. Okay. And a more detailed comparison or a fair comparison is try to plot in all the data in this phase diagram, which is the HC2 normalized by the Pauli paramagnetic limit. This dashed line here is the upper limit that is allowed for a BCS superconductor, and this is the horizontal axis is a TC normalized to the 0 field TC, and you can see that for the bulk material, the solid dots are actually the parallel field. For the bulk material, it goes like in a linear shape here, which is because of the vortex formation in the bulk material. And when you go to atomically thin materials, it goes into square root dependence, like that in a small field region, at the high temperature region. Okay. And then it goes way beyond the Pauli paramagnetic limit. And actually, we can do a simple fit to the data and try to extract the energy scale relevant to the system.
They're confusing here that so argument actually works in the monolayer, but once you move on to bilayer or trilayers, basically you just kind of break down this symmetry based on ideas, right? So there's no more of the Ising spins, like spin type of the locking is expected in the bilayer or trilayer, isn't it?
Yes, actually, very good question. I'll go to the next slide. I'll answer your question on the next slide. Yeah. You're talking about essentially why the 2-3 layers also go beyond, way beyond the dashed line. Yeah. So yeah, basically we can extract by the fitting pair breaking equation. We can extract a spin-orbit field about 700 Tesla, which is actually agrees pretty well with the first principle calculations of the Fermi surface. Okay, that's also related to your question in this slide. So that's the data about a year ago. After we publish our results, we can actually get access to the 45 Tesla hybrid magnets, we can actually now map out the full phase diagrams, at least for the bilayer and the trilayer material. And this is shown here, the dots. And you can see that both of them actually exhibit this square root dependence at the beginning, and then goes way beyond this Pauli paramagnetic limit here. And the reason, actually, even for this kind of materials, so my argument only holds for, as Philip mentioned, only holds for a monolayer material, but for this bilayer and trilayer material also goes way beyond the Pauli paramagnetic limit. The reason is actually that the interlayer interaction or the interlayer coupling energy scale is much smaller compared to the intralayer spin-orbit splitting energy scale. So that in that limit, the layers are basically decoupled. So for example, I give some number here. The interlayer interaction is probably on the order of 10 MeV, but the intralayer spin-orbit splitting, at least at the K and K prime pocket, that's about 100 MeV, the spin splitting. So in this case, you can sort of think of it, the two layers are basically decoupled.
What is the penetration length scaling along this z-axis?
Yeah, that's also a good question. It's about 100 nanometer.
So can I just kind of think about just the different limits and then just kind of Ginsburg-Landau type of the arguments to try to explain this?
Yeah, you can explain actually this square root dependence using the Landau-Ginsburg formalism, but you actually cannot explain the fact that it goes way beyond one. Because that's still, you can actually enhance the orbital limit a lot, but still finally when you go to the spin paramagnetic limit, you still get just this value 1 here.
Okay. In a multi-layer case, are spins and neighboring layers aligned or anti-aligned?
Anti-aligned. So in the bilayer case, you can think of it, the two layers are like 180-degree rotating, right? So that would be, when you look at the Fermi surface of the whole system, it's spin degenerate, but actually the spinors are locked to the layer. So it's a spin and momentum lock within each layer, and then the spins are also locked to each layer. Okay, then so far, I hope I sort of semi-convinced you that this is roughly the right picture. But then, as you're going to see in our most recent measurements, hopefully you will be more convinced that the picture here I presented is actually correct. But then I also asked this question: what are the other consequences or the interesting physical consequences for this kind of Cooper pairs with Ising spins? And in particular, I mentioned that the Cooper pair wave function supposedly is going to have a triplet component, and can we actually do some measurements and see some evidence of this spin triplet component. To discuss about the physics, let me just go back to some basics of BCS superconductor. Here I illustrate the block bands of a metal again with the Fermi energy by this dashed line. So in a BCS superconductor, really electrons with opposite spin and opposite momentum can pair up to form Cooper pairs, and then they condense to become a superconductor. And the energy gap is opened. This 2 delta here is opened at the Fermi surface. So this, on the right-hand side, I plot the quasi-particle density of states as a function of energy, and you can see that 2 spikes corresponding to this opening of the gap, the diversion of density of states. And the Cooper pair wave function in the BCS superconductor is characterized by this singlet pairing, spin singlet pairing with a spatial even wave function. And at the 0 temperature limit, when all the quasi-particles are frozen in the 0 temperature limit, the spin susceptibility of a spin singlet Cooper pair is 0. It's just meaning that the Cooper pairs are not responsive to an external magnetic field. So that actually gives rise to a first order transition in the magnetic field induced superconducting to normal metal transition. It can be seen by plotting the free energy versus the magnetic field in the 0 temperature limit. And the blue line here, actually I plot the normal state metal, which has a paramagnetic energy (-1/2 times the spin susceptibility times h squared, like this. For BCS superconductor, it does not respond to a magnetic field, so the spin susceptibility is 0. So in this case, ignoring orbital effect, then you only have the condensation energy, then it stays constant with the external magnetic field. So the touching point here defines the HP, the Pauli paramagnetic limit, and you can see that they touch at a kink, so that's the definition of the first order phase transition. And actually the whole phase diagram has been worked out by several theories, including Sama, Maki, Sunetto, and several others. And here I plot out the full phase diagram, the magnetic field versus temperature for BCS superconductor. And below a certain critical temperature here, not the critical temperature, below a certain characteristic temperature, T star here, the phase transition turns from a second order into a first order, like this, for the spin paramagnetic limiting case. This actually can be measured by tunneling measurements. If you can actually do a tunneling measurement on the BCS superconductor, you can measure the density of states like this. So you start from some low temperature, represented by this red dot here. As you increase the magnetic field, there's a Zeeman splitting for the quasi-particle density of states. So the spin up goes to your right, the spin down goes to the left here. But I want you to notice that actually the superconducting order parameter, or the superconducting gap, remains unchanged for a BCS superconductor. And if you keep increasing the magnetic field close to the phase transition line here, the spin up and spin down quasi-particle peaks almost touch each other. And when you go a little bit more, then it suddenly jumps to zero. It's a first order phase transition. So if you can measure the order parameter as a function of magnetic field at low temperature, you can tell whether it's a first order transition or second order phase transition. And this actually has been done not that far away from here by Maserfi and Tedrao for a few nanometer thin aluminum thin film. It's a BCS superconductor. On the left-hand side, I show the tunneling spectrum for this material. And you can see that with increasing magnetic field, the tunneling spectrum turns from one single peak into a double peak feature like this because of Zeeman splitting. And I also want to point your attention actually that even under very high magnetic field close to the critical field, the order parameter defined by the superconducting gap from here to here, this point, is almost unchanged. So that only when you go beyond this case, the gap suddenly closes, so the material turns into normal. So we would like to measure the order parameter in our material. And so this is actually showing a schematic of our device. We've just put many points so that if one junction breaks, we still can measure the other junction. And what we use is a platinum as electrode with a thin layer of aluminum oxide, and then put the material directly on top of these many electrodes here. And the experiment is basically by varying the Fermi energy of the platinum electrode, so that when the electron tunnel into this divergent density of states, the differential conductance is expected to give rise to a peak here. So this is the experimental result we've measured at 300 millikelvin and under different magnetic field. And you can see under zero magnetic field, there are two spikes corresponding to the divergent density of states. And differential conductance does not drop to zero here because of Andrea reflection, which I'm not going to go into the details. This is actually a point contact device rather than a tunnel junction device. As we increase the magnetic field, the first thing I want you to notice is actually that there's no Zeeman splitting in the quasi-particle peaks, which is completely different from a BCS superconductor. And this actually supports the picture that the spins of the quasi-particles are actually locked to the outer plane direction by the spin-orbit interaction. And secondly, you can see that the gaps are actually continuously closing with increasing magnetic field. And here I show, this is the phase diagram. We perform measurement at this temperature with increasing magnetic field here. I show the differential conductance plot in a contour plot like this. With increasing magnetic field, you can see that the two quasi-particle peaks come in continuously. So it suggests it's actually a second order phase transition. We can fit our spectra with the BTK formula actually developed at Harvard, and several different temperatures here. And you can see that basically at all temperature scales down to about 5% of the TC, the order of the phase transition looks like a second order phase transition in the whole phase diagram. So it's very different compared to a BCS superconductor. And lastly, I just want to discuss briefly how do we understand it. So in a noncentrosymmetric metal, with strong spin-orbit interaction, the spin-up and spin-down bands are actually split by the spin-orbit interaction by an effective spin-orbit field, HSO here. And electrons with opposite spin and opposite momentum can still pair up and form Cooper pairs, and still you have an energy gap like this, giving rise to two spikes in the density of states. And actually, the spin of these quasi-particle bands are actually locked to the outer plane direction by the spin-orbit interaction, so that when you apply in-plane field, there's no Zeeman splitting that can be observed in this case. And furthermore, the wave function of the Cooper pairs can be written down as a mixture of a spin singlet component and a spin triplet component. And a very nice way to illustrate this quantum mechanical spins of a spin triplet component is that even in the outer plane basis, it has zero angular momentum. When you project the two spin in the in-plane basis, it has actually a finite spin angular momentum. So what it means is that for even at the zero temperature limit, the spin susceptibility of this triplet pairing component is bigger than zero. It's actually non-zero in this case. So now the free energy actually gets modified into this form. I remind you again, this blue line is the normal state. The dashed line is the BCS superconductor. Now the superconductor of the Ising superconductor, because of the spin triplet component, it has a finite spin susceptibility, so it also responds to the external magnetic field. So you can see that they touch basically smoothly at a much higher magnetic field, so that it gives rise to a much enhanced HC2 as well as the second order phase transition of the superconductor. So this qualitative theoretical picture can actually be put down by our theory collaborator KT Law from HKUST. What he calculated is using a realistic initial band structure of an niobium diselenide and calculate the whole phase diagram. And you can see that it's actually the order parameter varies smoothly with increasing magnetic field. It's all second order transition.
In fact, in your band structures, there are multiple pieces of the band.
Yeah.
Right. So how should I just kind of think about which party is pairing to which? Actually, it's always pairing across the gamma point symmetrically.
Let me just go maybe where is the Fermi surface? Let me just go to the Fermi surface. Yeah, so this is the Fermi surface here. Basically, we have Cooper pairs from the gamma pocket, which is any momentum at this point coupled to this momentum at that point, as well as the K to K prime.
Okay.
So you actually can think of it, there are two kinds of Cooper pairs. One is the gamma point Cooper pairs, one is the K and K prime Cooper pairs.
What's the period of CW evolution?
That's about 3 times of the lattice constant. It's incommensurate, but it's about 3 times of the lattice constant.
So is there any break scattering because of that?
Yeah, in principle, if you go to the CDW case, you zone fold it. Yeah,
You don't have do you have CW or you don't?
We believe we have CDW. Yeah, actually, you can measure the Hall coefficient and also as well as the Raman. It shows that the CDW order still remains.
Yeah, so if it's 3 times bigger, it will produce coupling between these sheets.
Different band.
Yeah,
Sorry, don't understand. So, how is related the charge density wave order with the fact that you observe two kind of? I'm quite confused. With these two kind of Cooper pairs, let's say, because you have two kind of components, right?
I think.
You have two kind of electronic components.
Yeah, yeah.
And I don't understand if there is any relation with the fact that you observe this charge density wave order.
Okay, so as long as, according to my understanding of the bulk niobium diselenide, I'm not implying it's the same thing for the two-dimensional niobium diselenide. The CDW gaps are basically, the CDW order is quite decoupled from the superconducting order. Yes. The CDW gaps are only open up at a few points at the K pocket and the K prime.
So if there is the charge density wave order, or it's not, or if there isn't in your system, then you would anyway observe this. I mean, it's completely decoupled, so something completely different that you can also not take in account in your theory, or
I suppose still the spin orbit interaction picture should still be roughly there. I think it should be there. I mean, not roughly there, it should be there. So I think the picture should be more or less correct here. Well, okay, so yeah, this is a theoretically calculated phase diagram, and actually ignore the CDW order in this case, CDW coupling in this case.
In this calculation, do they assume that the triplet component does not change when you apply magnetic field, or is it this triplet component enhanced by magnetic field.
So yeah, actually it's enhanced by magnetic field. So the spin susceptibility is actually is smaller than the normal state spin susceptibility, but then it gets actually very close at high magnetic field, so that they can touch in a tangential way.
So it gradually evolves from singlet to triplet.
Yeah, you can think of it like basically the pairing correlation is that the triplet component would get more enhanced compared to singlet with increasing magnetic field. Okay, so I just quickly put up the summary. Well, we basically have observed this enhanced upper critical field, which is consistent with this picture of a Zeeman-like spin-orbit interaction, and it's supported also from measurement of the superconducting order parameter by tunneling measurements. And I will basically skip through. Well, maybe let me just mention this sort of interesting thing to you is the possible existence of topological superconductivity in this material. So here is the Fermi surface, and I mentioned that because of spin-orbit interaction, the Fermi surface is spin split, except there's actually several points on the Fermi surface at the gamma point, which so far I have ignored the effect. Actually, it has been calculated that when you apply a magnetic field in this material above the HP but below the upper critical field, the material turns into something called a nodal topological superconductor. You can sort of think of it in this way, that at these several points, the superconducting gap is not protected by spin-orbit interaction because these several points the spin-orbit field is zero. So that the gap would just close at these several points here. So it turns into a nodal superconductor, and it turns out that this is a rough picture I came up, is that if you apply a magnetic field higher than the HP, basically the gap, the bulk of the material is largely gapped except that several nodal points with some zero energy and Majorana modes on the surface of the material. So it's quite an interesting system to see whether this is the case in the future. Okay, with this I thank you for your attention.
You mentioned there are 6 combination of TMD metals. Do you expect to see higher TC in other type of TMD metal other than this?
As far as I know, the niobium selenide, the bulk material has the highest TC among them. But there is actually one interesting observation recently. For niobium selenide, when you decrease the layer number, the TC drops. But for tantalum sulfide, the TC goes from 0.5 Kelvin in the bulk to several Kelvin in a 2-3 layer material. So there must be something changing in that material. So maybe this electron-phonon coupling is changing with decreasing layer number.
Generally, if you have heavier elements, you will have stronger spin-over coupling and electron-phonon interaction. Why don't you see?
Okay. So when you go to heavier element, so one thing that would decrease TC from the BCS theory is that the Debye frequency would decrease. Right? So that would decrease the TC. But that may not be the major effect because the Fermi surface gets changed a lot when you go from niobium selenide to tantalum selenide, because in niobium selenide, the spin-orbit splitting is still very small compared to the bandwidth. The bandwidth is about 1 eV, the spin-orbit splitting is about 0.1 eV. But in the case of tantalum diselenide, the spin-orbit is half an eV, the bandwidth is also 1 eV. So basically, it's quite a dramatic change compared to niobium selenide. I think the strength of the electron-phonon coupling is quite much modified.
Other questions? I guess I have to have one. The Majorana, how would you know whether it's there or not? Do you have a way to?
I guess it would be nice to perform a thermal transport measurement because, for example, basically the Cooper pairs cannot conduct heat,
Okay.
but the edge modes can conduct heat.
Oh wow.
Maybe a thermal conductance measurement.
Yeah, but also for Majorana, I think in a 1D mode, right? So this is a 2-dimensional thing.
Yeah, this is a two-dimensional on the boundary.
Localized.
So basically, I think some theories that predict that you have to measure the thermal Hall conductance. But yeah.
you have this six points that the gap is closed, right?
Yeah.
And which is where you suspect the Mariana will come from.
Yeah, this is the bulk. This is the bulk band structure. But when they close, then the material will turn into a topological superconductor. So expected some edge modes will show up.
So, but there are 6 points at which it closes.
Yeah.
So if there's some kind of coupling, then that will potentially ruin the Mariana fermions. Is that right, or will you see like 6 degenerate?
Yeah. It's true. There could be some coupling. For example, I think something I can imagine is that if you put your material on the substrate that breaks the perfect out of the plane mirror symmetry, that could potentially actually destroy this point here because you induce a little bit of rush-bar spin-off interaction. Right, then the gap is not completely closed there.
Is there a way to prevent it, or
to prevent it? I'm not up to that point yet.
Okay, any last question? Yeah.
Yeah, for the mixture of singlet and triplet pairing in the presence of the field, what portion of the Fermi surface are mostly singlet and what portion mostly?
Yeah, for the picture, I've been talking about most relevant is K and K prime because it has the largest spin-orbit coupling. Yeah, so you can see actually the spin-orbit splitting is more significant at the K prime pockets than the gamma pockets.
So if you didn't have the gamma pocket, you would have majority of this triplet pairing, or you will still have?
You still cannot. We still don't have a majority triplet pairing. The triplet component, this number here, the dz here, a rough estimate is basically the spin-orbit splitting at the Fermi surface divided by the bandwidth. So in this case, it's 0.1 eV divided by 1 eV. It's 1/10 of it. So 1/10 compared to the
But do you always have singlet in the gamma pocket?
In principle, not, because you also have spin-orbit interaction. So you still get this component.
Only 6 points reversed.
Yeah, the 6 points. This component is gone at the 6 points.
Okay.
Sorry, I have a last question. Do you think this mixed pairing will give you some unique entry reflection in this?
Oh yes, I sort of skipped that. This is this one here. When you couple to a ferromagnet, actually, the Andrew reflection, the differential conductance due to Andrew reflection would depend on the magnetization direction, because you actually have this triplet component which is characterized by a d vector here, and the d vector is actually out of plane in this material, so that it depends on the relative orientation of the magnetization with respect to the d vector.
Okay, well, a very nice talk. Let's thank you again. And students in ES 294, you need to sign up.